reaction, it's also called the synthesis reaction, is probably the simplest of the reaction types. Essentially, we have two things coming together to form a new compound. So here we have substance A and substance B, the reactants, and when they react, we end up with substance AB. And that's a new substance, and it's going to have very different properties than either A or B. If we were to draw the whole reaction out, we'd have something like this. A plus B yields AB. An example would be iron, which is a solid, plus oxygen gas yields iron 3 oxide, which is a solid. Don't worry so much about the S or the G, but you can see the Fe and the O2 come together to form one substance. We want to balance this equation though so it obeys the law of conservation of mass, so that we have the same number of atoms on each side, and that would look like this. But again, don't worry about that. You're looking at two different substances coming together to form one. That's a combination or synthesis reaction. So if we had magnesium metal plus oxygen gas, those would combine to form magnesium oxide. That's your combination or synthesis reaction. And we could write it out like this. Again, don't worry too much about the S for solid or the G for gas. You can see the two substances forming one. And again, we balance this just to make sure that we obeyed the law of conservation of mass. So you can see here we have a strip of magnesium metal, and we're going to ignite that in air. And when we do that, the Mg and the O2 in the air will combine to form a new compound, MgO. It'll also give off quite a bit of light and heat at the same time. Again, combination reaction, we have Mg plus O2 coming together to form magnesium oxide. Here's the metal before, and then after the reaction, our MgO is a white powder with properties very different than the original Mg and oxygen.
Station with our favorite scientist Carl, and we're playing with methane gas today. I don't know if I want to play with that. What do you think?
And you're saying that probably because you're thinking of the odor, right?
Yeah.
Because methane is about 99% of what natural gas is. And so actually that odorant is something the gas company puts in to warn you of the methane. The methane I have here is completely odorless. So you won't be smelling anything as we work with this today. That does make it a little more dangerous though, because if you have a leak, you won't be able to know that you have a leak.
True.
All right. So what I'm going to do is I'm just going to bubble some of this methane gas into this tube that has a little bit of bubble solution in it, okay? And we're going to make some bubbles, and once I have a good number of bubbles, I'm going to have you scoop some up. But remember, you can't really easily pick up bubbles if your hands are dry. So what I need you to do is first is to dip your hands in that other tray of soapy water.
Okay.
That way you'll be able to gather up as many bubbles as you can. Now remember, this is a flammable gas you're going to be holding in your hands. Okay, so I recommend you hold it away from your body, and let's get a little bit more.
Oh, okay.
More is always better.
More is better. Come on,
Okay,
Carl.
so try to scoop out as much of that methane as you can.
And just put it in one hand?
Just put it in one hand. One hand will be far more interesting. Now, methane is lighter than air. Okay? Now, we don't have big enough bubbles here to make it sort of float away, but what we can do is light it on fire. All right, so I'm going to take a match here.
In my hand.
In your hand, and we're just going to light this methane gas on fire. 3, 2, 1, there we go. Now, the cool thing, besides that big pillar of flame, is the fact that your hand is not burnt, right?
I'm still shocked.
Okay, so your hand is not burning. And so the cool science here is that water has a tremendous ability to absorb heat.
It's a little warm.
Did you feel the heat from that?
Yeah, I sure did.
You probably felt it on your face as well. Now, water has a tremendous ability to absorb heat, and that's what protected your hand. Also the fact that, you know, in order to burn your hand, we'd have to like boil that water off and then singe your hand, and
thank goodness
that
we
did
didn't
not
do any
happen.
of
That did not happen. And certainly we also want to recommend that you don't try this at home. This is just, you know, for us here.
I just happen to have a bunch of methane.
I just happen to have
no
some
one has
methane
any of
at
that
the Science
Thank
Center.
goodness, but this is really neat.
But again, it also goes to the idea of firefighters when they have to fight fires. Not all fires hug the ground. Okay,
Right.
some of the flames can actually be floating up in the air, like this pillar of fire you're about to have in your hand. And firefighters actually use methane in this way to sort of practice fires that are a little bit tricky. Just use one hand. Just burrow down in there. Just burrow down in there.
All right.
And so you can imagine this pillar of fire happening inside a building, hitting the... hitting the ceiling, transferring across the ceiling, and that's just an added bonus there that we get it. We got rid of the extra
Just
methane.
throwing that fire all over the place.
You're getting
Carl,
kind of crazy.
so much fun. I'm sure everybody at work wants to do this too.
Iron powder and sulfur powder react together extremely exothermically. For this experiment, only iron and sulfur powder is needed. The amount that you need will depend on how much you want to make. You can make any amount as long as you maintain the mass ratio of 7 grams of iron to 4 grams of sulfur powder. First, I added 35 grams of iron to 20 grams of sulfur. I then poured the powder between each beaker back and forth until the mixture became relatively homogeneous. When mixing two reactive powders, this is often the best method to use. Mechanical stirring, or even worse, grinding with a mortar and pestle, could lead to the spontaneous ignition of the mixture. You might notice that there are still quite a few clumps of sulfur in the final mixture. For our purposes, this is okay. However, if you wish to avoid this problem, simply use dry sulfur and fully powderize it before using it. Now that we are done mixing the powders, we are ready to react them. The best and most impressive way to set off the reaction is to simply heat up a glass rod and place it into the powder. The temperature of the glass stirring rod only has to be a little over 100 degrees, which is the melting point of sulfur. When the sulfur melts, its reaction with iron will begin. So the reaction that's going on here is actually quite simple. Simply put, the solid iron and the liquid sulfur combine to form iron 2 sulfide in an extremely exothermic reaction. This reaction should only take place on something that can withstand the high heat. This means it should be carried out on something like concrete or a high melting point metal, not aluminum, because aluminum will melt at around 600 C. Also, absolutely no glass, porcelain, or organic polymer of any kind. This reaction is interesting, but the final product, iron 2 sulfide, is actually a useful product. The iron sulfide from this reaction can be collected and reacted with hydrochloric acid to produce hydrogen sulfide gas. It has a rotten egg smell and it is extremely poisonous. Its toxicity is comparable to that of hydrogen cyanide. However, despite its significant toxicity, hydrogen sulfide gas is used in a multitude of chemical processes. I'm providing this video to show you why you should not carry out the reaction on glass or porcelain. The reaction is extremely exothermic and it can easily crack and shatter glass. In the end, you are left with a very hard, dense material that is stuck to the end of the glass stirring rod. If you are interested in keeping the iron 2 sulfide, then you can wait till it cools, break it up, and put it into a container. Just as a warning, powdered iron 2 sulfide is pyrophoric, which means that you probably shouldn't powderize it as it might ignite on contact with air.
When we place the element zinc in hydrochloric acid, it reacts, forming zinc chloride. The reaction also produces bubbles of gaseous hydrogen.
On its own. Now, a big part of the reason why this isn't a spontaneous reaction is because sodium and chloride over here are really happy with the number of electrons that they have. Sodium doesn't want to gain more electrons, and chloride here doesn't want to lose electrons. They're totally set right here. So we have to force this process to happen, and that's where the electricity part of electrolysis comes into play. The electrical energy from a battery can force this process to happen. So here's our battery, and a battery has these two sides, the positive and negative. The positive side of the battery pulls electrons in. And the negative side of the battery pushes electrons out. So these two things can force this process to happen. So chloride doesn't want to lose its electrons. But you know what? The positive side of the battery just pulls electrons away from it, right? It's like, you don't want to lose these electrons? Tough. I'm just going to pull them away from you. And the negative side of the battery that pushes electrons out, it's going to push electrons to sodium. Sodium doesn't want to gain electrons? Too bad. The negative side of the battery is going to push electrons to the sodium, making this process happen. So now, I want to show you the device that we use to do electrolysis and make this process happen. And then I want to use our atomic vision to see the atoms and electrons and how they move during this electrolysis process. So here's a picture of the device that we use to make this process happen. This is called an electrolytic cell, and it's got a couple of different parts. First, we got this container that's full of the sodium chloride. Then we got a battery, and the two sides of the battery are hooked up to what we call electrodes. The electrodes put electrons into the sodium chloride and they pull the electrons out. And then finally, the sodium chloride here, it's not just like the powdered table salt that you're used to from the kitchen. This has got to be molten, liquid, melted sodium chloride. Sodium chloride doesn't melt until about 1500 degrees Fahrenheit or 800 degrees Celsius. So it's got to be super, super hot. And this device has to withstand really high temperatures. The sodium chloride has got to be molten for the electrolysis to happen. Now let's zoom in on this a little bit more. If we could zoom in to the sodium chloride millions and millions of times, this is what we'd see. The sodium chloride is molten or liquid, which means that the sodium and the chloride ions have come apart from each other and they're in constant motion moving around in this container. Now, here are the electrodes. This is that one, and this is that one. These electrodes in the diagram here are way, way, way closer together than they should be based on this. This is definitely not to scale, but I wanted you to be able to see both of the electrodes. Now, there's another important part of this electrolytic cell, and that is the battery. The diagram that I put here shows the direction that electrons move. Electrons move from here into the battery and then out of the battery into this electrode. So we can give names to these two electrodes based on how the electrons are moving, okay? The electrode over here we call the anode. The anode is the site of oxidation. Oxidation is happening in here because the anode is pulling in electrons, because this is the direction that the electrons move. Now over here, we have the cathode. Reduction happens to the cathode. The cathode pushes out electrons because this is the direction that electrons are moving from the battery. So we got the anode and the cathode. We got the battery, the electrodes, and the sodium chloride. We're ready to do some electrolysis. I'm going to get rid of a few of these ions to make the process a little bit clearer. Okay, that's a little bit clearer. So now, we hook the battery up to the electrodes, and this is what happens. So this cathode here is connected to the negative side of the battery, so that means that it's going to have a negative charge. These positively charged sodium atoms are going to be attracted to the negatively charged cathode because opposite charges attract. So we got this Na plus moving over to the negatively charged cathode. And electrons, as we said, are being pushed out of the battery into the cathode. And this electron is going to be given to the Na plus ion. And gaining that electron is going to get rid of the charge on that Na. So it's going to turn this into a neutral sodium atom. The same thing is going to happen to this one over here. It's got a positive charge, it's attracted to the negative cathode, moves over here, an electron gets pushed from the battery, it goes into the sodium ion, and gaining that electron causes the sodium to lose its charge. So now we have two neutrally charged sodium atoms. Now over here at the anode, the opposite thing is going to happen. Electrons are going to be pulled out of these ions. So we got this chloride over here. It's attracted to the anode because the anode is hooked up to the positive side of the battery, and this is negatively charged, so it's going to be pulled over here. And the anode is pulling in electrons, so one of the electrons from the Cl- is going to be pulled up towards the battery, and that is going to cause the negative charge to go away because it's lost one of its electrons. And then over here, this Cl- is also going to get attracted to the anode. It's going to lose one of its electrons. It's going to get pulled up here towards the battery, and that is going to cause this to lose its negative charge. Now we said that chlorine here is one of the diatomic elements, so that means that we're never just going to find one of these atoms on their own. As soon as they don't have a charge anymore, they're going to pair up to form a Cl2 molecule. This is gas, and it's actually going to float away. So that's how the electrons move in this electrolytic cell. Here's a diagram of the process that I just showed you. I want to use this to write half reactions for what's going on at the anode and the cathode. So oxidation happens at the anode and reduction happens at the cathode. Let's write these half reactions. So over here at the cathode, we start out with Na1+. That gains an electron, plus E-, the symbol for electron, and that gives us neutral sodium, Na, without a charge. That's how we know it's neutral. Now over here at the oxidation half reaction, I'm going to write this a little bit incorrectly first, and then I'm going to fix it. Okay, so here we start out with two Cl1-, okay? Two Cl-. And then what happens is these lose two electrons, 1, 2, get pulled up to the battery. So I'm going to write -2E-. That's incorrect, but I'll fix it in a minute. And that gives us a molecule of Cl2 gas. Now what's wrong about this? Well, you can't subtract things in a chemical equation, even though it makes a lot of sense. So to make this correct, I have to put these two electrons on the other side of the chemical equation. So here is the correct version, where I've just moved the electrons over here. And this is the correct way to write the oxidation half reaction. Now that I've written the oxidation and reduction half reactions, I want to show you how we can put them together to get a reaction for this whole process. Now let's combine these half reactions that we just wrote. In order to add or combine these half reactions together, they have to have the same number of electrons, but they don't. Right now there's one electron here and two electrons here. So to fix that, I'm going to take this reduction half reaction and I'm just going to multiply it by 2, just like it's a math equation. And that is going to give me this new reaction. I've just put a 2 in front of everything, distributing it across the reaction. Okay, so there's my new reduction half reaction, and then here's my oxidation half reaction. Now that they have the same number of electrons, I can add them together. And this is what I get. I take everything on this side of the arrow and put it on one side. I have my Na, my 2 electrons, and my 2 Cl on this side. And then on this side, I have my Na, my Cl2, and my 2E-. Now there's still a little bit more that I have to do before this equation is totally finished. If there's anything on both sides of the arrow, we cancel it out. So there are 2 electrons here and 2 electrons here. I'll cancel those out. And then I have 2 Na+ here, and I have 2 Cl- here. I can combine those together to make NaCl. So my final equation is going to look like this. 2 NaCl, and then on this side, 2 Na plus Cl2. And you'll notice that I've also put in these parentheses to show the physical state of each of these particular compounds. This is liquid because it's so hot, it's molten. The Na is also liquid because it's so hot. And the Cl2 is gas and just floats away. So let's just pull everything together that we talked about. Here is our final equation for the electrolysis of sodium chloride. This happens because sodium gains electrons and is reduced. This happens at the cathode in the electrolytic cell, which pushes out electrons. It's where reduction takes place, and it's where sodium gains these electrons. Here is the half reaction for the reduction of sodium. Then chloride loses electrons. It undergoes oxidation, and this happens at the anode in the electrolytic cell. The anode pulls in electrons, oxidation happens there, and here is the half reaction for chloride losing electrons and getting oxidized. So that's how sodium chloride turns into sodium and chlorine gas during electrolysis.